Hello friends, the next topic in 555 timer and application is the Astable Multivibrator using 555 timer. Now we will discuss the very important application of 555 timer, that is Astable Multivibrator using 555 timer. Here pin number 2 and 6, please see carefully. This is pin number 2, that is input of comparator 2, and pin number 6 input of comparator 1, both are short circuited. Pin number 1 and 5 are connected to ground. Of course there is a capacitor in between. Pin number 4 is connected at VCC. When pin number 4 is not used, it is connected to the supply, remember this, so that this Q2 remains off, right? And pin number 7 is connected at the junction of two transistors. Now let us see the operation. I will draw the waveform. Let us see the output. This is voltage across capacitor. The voltage across capacitor will vary between two levels. What are those levels? Voltage, you please see 2 and 6. So voltage reference for pin number 2 is what? VCC by 3, and voltage reference for pin number 6 is what? 2 VCC by 3. So voltage across capacitor varies from VCC by 3 to 2 VCC by 3. This is voltage across capacitor VC, right? And now we will see the operation. So it's like this. Voltage increases initially when capacitor is charging. During charging period, the voltage across capacitor increases from VCC3 to 2 VCC3, like this. During this period, output is high. I will explain why it is so. Then when voltage across capacitor reaches at VCC by 3, so I will explain operation from this point onwards, so please understand. When voltage across capacitor here becomes or try to become more than VCC by 3, that is at pin number 6 or 2. So when voltage at pin number 2 and 6 try to become more than 2 VCC by 3, so if this voltage is more than this output becomes high, this output is low. Why? Because voltage at this node is VCC by 3, this is 2 VCC by 3, so this voltage is more than this, so output of this comparator is low, output of this comparator is high. The moment output of this comparator is high, R is high, Q bar becomes high. The moment Q bar is high, this is inverter, so output becomes low. So from this point onward, output of the circuit becomes low, right? And the moment output becomes low, this is high because this was high, reset was high, Q bar is high. The moment Q bar is high, this transistor Q1 is shorted because it is saturated. It is driven to a saturated state, that means transistor Q1 is turned on and pin number 7 is connected to ground. So that pin number 7 is connected to ground internally through the transistor Q1. So pin number 7 is connected to ground internally to the transistor Q1. Now please see carefully, this point is at ground potential, so capacitor starts discharging through this path, like this. From here to here, capacitor starts discharging and capacitor starts discharging. So during discharging period, please see carefully, output of this circuit is low, right? Output of the circuit is low. During discharging period, what is the time constant of the circuit? The time constant of RC circuit, only one resistance is there in RC circuit during discharging period, that is RB. So time constant of the circuit is RB into C. Time constant during discharging period is RB into C, right? So this is, suppose discharging period is TD and charging period is TC. TC now we will see in the next part, right? The moment voltage across capacitor, now the capacitor is discharging, the moment voltage across capacitor falls below VCC by 3, the voltage across capacitor falls below VCC by 3, so voltage at pin 2 is trying to fall below VCC by 3, so this voltage is less than 2 VCC by 3, So output of this circuit is definitely low, but when voltage at this circuit falls below VCC3, the output of this comparator becomes high. The moment output of this comparator becomes high, Q bar becomes low, and Q bar becomes low means this transistor is turned off and output of the circuit becomes high. So from this moment, the moment it reaches here, output of the timer becomes high, and the moment this was high, this was low, the moment the input to the transistor is low, this is isolated. This means pin number 7 is disconnected from the ground by the transistor, because transistor is driven to cutoff state. So, and when the moment it is disconnected by the transistor, again capacitor starts charging through RA and RB, and capacitor starts charging through RA and RB. At certain point of time, voltage across capacitor reaches to 2 VCC by 3. Voltage across capacitor reaches at 2 VCC by 3. Again, when voltage across capacitor reaches at 2 VCC by 3, this output of this comparator circuit becomes high. When this is high, this is high, this is connected to ground, output becomes low. So output becomes low and capacitor starts discharging through transistor Q. So this is charging period. So during charging period of the capacitor, what is the time constant? We have two resistances in the circuit. During charging period, current flows like this, and during discharging period, current flows through this. So this is RA plus RB into C, right? These are time constant. The tau is what? This is time constant. That is time constant during which period? During discharging, that is during discharging period, right? And what is this? This is time constant when? This is time constant during charging period, right? This charging period. I hope this is clear. Now remember, the time constant during charging period is given by time constant during time period, this period. The time period during charging period is given by time constant of the circuit into natural log of 2. Similarly, time constant, and that will be equal to what? RA plus RB into C multiplied by log of 2, right? That is log of 2. And discharging period is time constant during discharging period multiplied by natural log of 2, that is RB into C ln 2, right? So this is discharging period, this is charging period, and total period is nothing but period of the wave generated at the output, and you will find a continuously running square wave, or you can say rectangular wave, at the output of the timer. Now the total period, if you take the total period of this, is nothing but, you can add these two, that is charging period plus discharging period. So that is equal to RA plus 2RB into C into natural log of 2, and that natural log of 2 is nothing but 0.69. So that is 0.69 RA plus RB twice RB, not RB, twice RB into C. This is very important, and if you want to find, this is very important, try to remember, because you have many questions, objective type questions based on this in exam. This is again very important, charging and discharging period. So you should remember these formulas directly, right? I have written it directly because that we have already seen in which topic, in astable multivibrator. You can refer that, right? My video on astable multivibrator using operation amplifier. So if you want to find frequency, so frequency of this is 1 by T, so that is 1 by 0.69 RA plus twice RB into C, that is the frequency. And when 0.69, when you take it in numerator, so that comes out to be 1.44. So you can remove this, or that is equal to, you can remove 0.69 from the denominator, and that is 1.44. This is the frequency of output of the Astable multivibrator using 555 timer. So Astable multivibrator, where do we use? Astable multivibrator is used for generation of frequency shift keying and pulse width modulated wave. These are two applications where we can use Astable multivibrator using 555 timer. So that finishes the Astable multivibrator using 555 timer. So in next video I'll be talking about monostable multivibrator using 555 timer. So wait for my next video. Thank you very much for watching the video. Now let us see the example based on Astable multivibrator using 555 timer. The first question here is an Astable multivibrator circuit using IC 555 timer is shown below. Assume the circuit is oscillating steadily. The voltage across capacitor varies between. This is a simple circuit based on 555 timer, and we know the voltage across capacitor varies between which values, that is VCC by 3 to VCC by 3 into 2. So VCC is 9 volt here, so definitely it must be varying from 9 by 3 to what? 2 into 9 by 3. So this is nothing but 3 volt, right? And this is nothing but 6 volt. So it must be varying from 3 to 6 volt. Which is the answer? Answer is B. So this is a simple question. Now let us see another example. Astable multivibrator using 555 IC is given in following figure. The frequency of oscillation is, you please see the circuit here. Now we are not given R and C elements in between pin number 8, 6, 2 and then ground. Of course, we are given a current source which is of value how much? That is 5 milliampere, and then we are given capacitor of value, that is C equal to 0.1 microfarad. So we are given these values. Now let us see how to proceed. You can see the solution here. I am given the current source, so we know the current through the capacitor, expression of current. I have drawn the internal circuit. You can please see this is the internal circuit. I have comparator 1, comparator 2, the control flip flop. Then we have power amplifier. This is power amplifier. It's not basically you can write it like this. This is power amplifier. Then we have transistor Q1 and Q2, right? But remember the voltage definitely varies from plus 1 by 3 VCC to 2 by 3 VCC. So in terms of current source, this DC current will be definitely flowing through the capacitor. There is no other way, because current entering into inverting or non-inverting terminal of an op-amp is 0. So this DC current of 5 milliampere flows through this capacitor and goes to ground, and we know the voltage across capacitor is given by, that is 1 by C integration of current with initial voltage added to it. This is the expression of voltage across a capacitor. You should remember here I is given to you. You can make it capital I, because in the diagram we have been given that's capital I. So I can take it capital I instead of small I here. So this is current is 5 milliampere, right? Capacitance is given to you. Initial voltage, remember the voltage across the capacitor varies like 1 by 3, then 1 by 3 or VCC by 3 and 2 VCC by 3. This is the variation in capacitor across the capacitor due to these internal op-amps. So then it comes to ground, then again like this, comes to ground, again like this, because how it is going to happen. Please see it carefully. When voltage at this point V2 becomes how much? 1 by 3 VCC, right? Less than 1 by 3 VCC I will say. When voltage at this point becomes less than 1 by 3 VCC, this comparator output becomes high, the flip flop is set. So output when flip flop is set, output of the flip-flop becomes 0 because this is Q bar, output is Q bar, so it becomes 0. When it is 0, so this BJT will be isolated, and when it is isolated, so nothing will be happening now, right. When voltage across capacitor become 2 by 3 VCC, see it carefully, when voltage across capacitor becomes 2 by 3 CC, so voltage here, the output of the this comparator becomes minus Vsat, so nothing will happen here, but output of this capacitor, this inverter becomes plus Vsat, and this is a reset. Output of flip-flop becomes 1. When it becomes 1, this op-amp is driven to saturation, so it behaves like a short circuit, and this point basically this point through the capacitor, through the transistor Q1 is connected to ground, so capacitor is suddenly discharged. Up to which level? Up to 1 by 3 VCC, because the moment a voltage at this point becomes plus V by 3 VCC, this is set, this becomes 0, and this is open switch. So initially voltage due to current source rises to V by 2 by 3 VCC, but the moment it reaches, it suddenly falls because of the shorting of the capacitor to 1 by 3 VCC, and this transistor is turned off. Again capacitor charging, and you have which type of signal? Sawtooth signal. This is basically this type of signal at the where across the capacitor. This is VC, right? Fine. And output is going to be of course a square wave only, because output of the flip-flop is changing from 0 and 1. Accordingly, I have 0 and 1, a square wave. So that's why we call it as free running oscillator. Now come back to the point. Here if you see this portion of the output from here to here, the output voltage, voltage across capacitor is varying from 1 by 3 VCC to 2 by 3 VCC. So initial voltage, if you start from t equal to 0, initial voltage across capacitor can be considered to be VCC by 3. So you put the expressions here in this, you will get the voltage across capacitor, right. Here VCC is given to be 5 volt. So VCC is given to be 5 volt. At t equal to capital T, means this time at t equal to capital T, what do we have? I have VC is 2 VCC by 3. So you put t equal to capital T here in this equation, put 2 by 3 VCC on the output side. So this, at t equal to 2 by capital T, this is 2 by 3 VCC. So to put capital T here, so you get this equation, right. So by solving this, you get this, and VCC is given to you, so you are able to get frequency of the wave at the output. That comes out to be 30 kilohertz. Now let us see the next question. The astable multivibrator circuit is shown in the figure below. If RB is shorted, if this is shorted, the waveform is, remember, when this is shorted, it will be giving me nothing but the voltage will be varying from 1 by 3 to 2 by 3 VCC. So that will be your output. That is a simple question, just like what we saw in the previous case. Fine, that has been explained here. Then let us see next example. The circuit of the figure shows a 555 timer IC connected as an astable multivibrator. The value of the capacitor C is 10 nanofarad. The values of RA and RB for a frequency of 10 kilohertz and duty cycle of 0.75 for the output voltage waveform R. You are given frequency, so frequency is given by this, right, and duty cycle of the astable multivibrator is given by this. So remember both of these expressions. So just by putting the values here, you are able to get values of RA and RB. That is the simple question, and that finishes your astable multivibrator using 555 timer. In next video, we will be seeing the monostable multivibrator using the 555 timer. Thank you very much for watching the video.